Our seminar. Our today's speaker is Alexey Umnov from Joint Lab High School Economics, Sberbank, and he'll tell us about recent developments in attempts to build Bayesian formulations of generative adversarial networks. This is the topic which I personally find quite promising, and I expect that we'll manage to build Bayesian formulation of GANs pretty soon. And these are one of the first attempts. So the talk will consist of two parts. First we'll review, well, Alexey will review AlphaGANs and then so-called BayesianGANs, although in these BayesianGANs there are some problematic issues, but anyway. So Alexey, please.
Yeah, thank you. So first, before giving you the plan of my talk, I'm going to briefly introduce Generative Adversarial Networks. You're probably familiar with them, but just to have clear notation to remember what it is. So our goal is to learn a data distribution. We have some data we can generate from this data. We want to learn to generate similar samples. So in order to do so, we create two networks, the generator network and the discriminator network. And the first one just takes latent variables, passes them through network, and outputs as a result. And the second one is a discriminator, which tries to understand which image is fake, which is real. In this generative adversarial network architecture, we have two objectives that we need to learn. First one is for the generator. Here, the first one is for the discriminator. Well, it tries to distinguish between real and fake images. The second one is for the generator, which tries to fool the discriminator. So what's good about GANs is that they generate quite sharp and clear images. Here's the comparison of some like classic architecture DC GAN with Variational Auto-Encode images. And this is not quite surprising because we know that contemporary convolutional networks can easily discriminate between high quality and low quality images. Well, they can distinguish between blurry images and non-blurry images. So the generator has a signal that it doesn't need to, it mustn't learn blurry images. But there are some problems with GANs. Like I'm targeting these two huge problems. First one is the mode collapse. Sometimes generators learn to generate not the full range of images that they can generate, but focus on small modes. Like here you can see some similar images that are generated from very different latent codes. Well, this behavior have many different explanations. The most simple one is that the discriminator doesn't see many images in the same time. It just sees one image, and it can have some penalty for this. So it sees one image, it's good looking, okay, the penalty is low. Another problem with GANs is that they are very hard to train. There are usually some instabilities, you need some hacks and tricks to meet the convergence and so on. So I'm going to present these two architectures, AlphaGAN and BayesianGAN, which take some steps into fighting these problems. Here are just the ideas of this architecture briefly, and then I will explain them in more detail. So the AlphaGAN takes this GAN architecture and Variational Auto-Encoder architecture, and they try to merge them in one generator. This is done by introducing intractable likelihoods in Variational Auto-Encoder and then fighting it with discriminators. I will tell you soon about it. And the BayesianGAN approach suggests to use not one network to generate samples, but a distribution over networks. And then you will probably not have this mode collapse problem, because if each network will represent a different mode in your data, and if you want to generate data, you first generate a random weight, and then using this weight generate your samples. Yeah, and I wanted to say that these architectures and this talk is not about some impressive images, impressive results on some data. It's about how you can use this Bayesian approach to improve your models. So, well, there will be some results and images, but do not compare with them with, do not look at only them. So first is AlphaGAN, and starting with a reminder what is Variational AutoEncoder. So we have data distribution, you have latent variables distribution, usually you can take it as Gaussian distribution, and you want to learn to posterior distribution encoder and decoder. First one taking the latent variable and introducing the distribution over your data, and second one in reverse, taking your data point and introducing the distribution over latent codes. You optimize it by maximizing likelihood, which is unfortunately intractable, so you need to introduce this lower bound, which you optimize instead of it. So I think I don't need to go into detail of this one, right? Common theme. So now, how do we optimize this lower bound? We make some assumptions on our likelihoods. So the posterior distribution, the encoder posterior distribution, is just normal distribution. For example, a normal distribution around the output of some network, and the decoder distribution is again normal distribution, and we have some networks that input the data and output the expectation and covariance. So now, if we make this assumption, we can plug these distributions into the formula above, and the first term becomes just the reconstruction error, like L2 reconstruction error. Is that clear? Why is that? Well, okay. And the second one becomes like something tractable. You have two normal distributions. You need to calculate chiral divergence between them. You just calculatable using these parameters. So now the good thing is that this lower bound is tractable. You can optimize it, find your encoder network, decoder network parameters, and your variational autoencoder is learned. But the problem is that we assumed here these normal distributions, which may be not the case, which may be a very strong assumption. And some people claim that variational encoder generates those blurry images just because we use normal distributions here. So maybe we can improve.
Here where? In encoder or decoder?
Both. Oh, well. There are claims for which one, I think. Yep.
Do you have any further ideas why using normal distribution in the decoder could be bad? I mean, in the end, you're modeling the marginal of likelihood as an infinite mixture of normals. So it looks like it might have a pretty huge expression power, expressionability.
You mean like there is ultimately all distributions that we can represent using this?
I mean, all we care about is having a good generative model. It's the good model of our axis, observed data. And in this model, in the variational autoencoder model, that would be a marginalizing of our decoder over the latent space, over the prior of Z. And this is essentially an infinite mixture of Gaussians. This looks very powerful to me. I mean, I guess in theory, I would expect it to be able to represent any distribution at all.
You mean about in encoder or in decoder?
Well, I think I mixed here the encoder and decoder word, right?
Yes.
Like if you
Yeah.
yeah. So the first one is decoder, the second one is encoder, and we want to learn this one for generation. Yeah. So now, do you still have this question?
Especially this one is problematic because it kind of suggests averaging in the image space, and averaging in the image space leads to blurry images. So it's
like here, right?
Yes. So basically, you don't want to put Gaussians in pixels.
Yeah. Well, we can put some different
Why don't
distribution,
you want
but
to
it's
put
there's
Gaussian?
still yeah.
But you don't want to average Gaussians, like but when you want, basically Gaussians are very connected with the averaging, because estimate the mean is average. You don't want average pixels.
It depends. Why not? What if you have just some tiny noise on pixel intensities? For example, consider taking a photo using a camera. Don't you expect the individual pixels have some noise, thermodynamical noise.
But it's very small noise.
Yeah, but
I think this likelihood assumes that pixels are independent, and we want pixels to be dependent, so Gaussian likelihood is.
But they are conditionally
Vectorized
independent.
Gaussian likelihood is not that good.
Yeah.
Right, exactly.
Yeah. That's factorized.
This is probably one of the main reasons. Maybe not the only one, but one of the main.
So you think that like if there was like structured covariance, then
Right.
it would be better?
Exactly. This is my hypothesis.
Okay.
Well, I heard that this part, and I heard this too, because we're averaging in the latent space, like projecting very different images into overlapping parts of Gaussian like bells. Just an intuitive explanation, I don't know. So, like, our goal now is to remove these assumptions and make the likelihoods more general. So, in order to do so, we introduce this density ratio trick. Consider just a GAN discriminator. It tries to discriminate between real and fake images, and we can look at it like assign some labels to the data. The label 1 is real data, label 0 is fake data, and now we have these two distributions, conditional distributions on the labels. And the discriminator usually doesn't predict like 0 or 1, it predicts the probability of real data. And if you want to calculate the ratio of your densities, density of the real data and the density of your model, you can do this just by simple transformations, like swap this to apply Bayesian rule to swap conditionals, and then you get the ratio of the discriminator probabilities. Well, here we assume that real and fake data have the similar prior probabilities. So, if we need to calculate the density ratio, we can do this trick just using the values of your discriminator. How does this help in our likelihoods? Well, we need to transform them a little. First, we look at the first part, add and subtract this real data probability. You get two terms. First term is the ratio of probabilities, and the second term does not depend on the theta parameters.
It's
So,
constant
yep.
with respect to theta.
Yeah, so now we can optimize this first term with respect to theta using just this value. And this value can be calculated if we learn the discriminator, which discriminates between real and fake data. Okay, is everything clear now? Well, next we do the same thing with the second part. It is even easier because we have Keil divergence of two probabilities. We rewrite it as an expectation of logarithm and get this ratio, which can be calculated using discriminator, which takes latent codes produced by prior distribution, takes latent codes produced by encoder distribution, and compares them which one is fake, which one is real. And again, here this ratio, we can estimate it and plug it into our second term.
C stands for what?
C is the discriminator for the latent codes. So now we learn not one discriminator, but two. One in the real space and one in the latent space.
Mm-hmm.
So now we have the choice for two types of likelihood. First one is using some distribution, some fixed distribution, like it was normal distribution on the previous slides. The authors of AlphaGAN suggest Laplace distribution, which results not in L2 norm, but in a L1 norm. And in other cases, it's just similar. Well, they suggest that L1 norm is somehow better for generating images. I think so. There are some other works on GANs that found this result too, but there is no clear explanation why is this. So, so this objective is like Variational AutoEncoder objective. It is probably it probably helps us with the mode collapse problem, but have those bad things I talked about before, like blur images. And the second choice is using the density ratio trick, which results in objective like in generative adversarial networks, which gives good samples quality, but maybe you can have more collapse. And the author suggests to just combine those two likelihoods in the sum and optimize them both.
Sorry, and
Yep.
don't the problem come from the fact of using one of those? So like, can it happen that if you combine both, you get both?
Well, I think we should look at it like this. Each objective fights some problem, and optimizing it and having it small, we will have small problem. Something like this. So if you sum them and optimize them both, you probably both of them will be small. And this somehow helps. But this is a good point. I think it is still detailed.
Well, the
So
first
basically,
one,
is it like you have your likelihood, which is conditional likelihood, or like marginalized likelihood, and then you just represent it as a sum of two terms, and for one you do like one approximation, for another you do another approximation.
Yep.
So basically just like you represent the same thing as sum of the two halves, which are identical, and then you do like two different equations for the two halves. Is it like that? Or like,
Yeah, something like that. But you can look at this like in different way. You can look at like you are optimizing the GAN, and this is just a reconstruction error, which suggests that everything is in your data is like grounded in everything on your latent space is grounded in the data. So each data point should be reconstructed well. It makes like latent space more diverse, the generated space more diverse. So you can look at it like we have a GAN, and it's improved with this one, or maybe this one improved with this one. Probably it helps with some problems.
yeah, it's really hard to have mod collapse in this formulation if you use the first term, because then it would have infinite loss if you completely miss some area.
Yeah, that's true. But, well, I think it still can collapse
Why?
in some
why do you
small
think,
way.
why are you saying that it can't not collapse? Because like all these like losses in the pixel space, they are kind of bounded from above, so it cannot be like too bad, because pixels have limited range.
Yeah, well,
so it's
something
like,
like
it
that.
can't be like too bad. And
So-
because people have done several times with GANs, like this, like adding losses in the pixel space, and this never helped. So it always led to blur images. The result is the same thing. Especially like for conditioning, for the conditional settings.
Well, yeah, by combining them, we hope that we achieve this. So answering the question about mod collapse, yeah, you have some training images that are not represented well. Well, they have higher, other images have lower. You cannot do anything more. Yep.
Please go back to slide number 11.
Yep.
I'm a bit confused by the way you actually train these. Like when you do density ratio trick, what do you train for?
You mean why did this generate?
Okay. Specifically, I'm confused by the fact that you don't have some sort of expectation over the p star of x or something like that. I mean, as far as I understand, when you train the same thing in GAN, you actually take samples from your synthetic distribution and from the real distribution, right? But here you only take the samples from the synthetic one, right?
Yeah, I meant that this we're working with the thing inside brackets. So when you optimize, you add this exploitation over data too. So it's like the first term here. Now we combine the second term and then the expectation over everything.
So we add the expectation over true data, right?
Yeah, I think I should go to the final architecture like this. Oh, no, there is no expectation here. Never mind. So there is expectation over all the data.
Okay, I'm thinking about this density ratio trick in terms of training some logistic regression where we have samples of two classes and then we try to push the probabilities in the correct way, right?
Yeah.
So you should have expectation over two different distributions, and those two need to be different. And I'm not seeing how it happens in this case.
Well, you're asking how we train discriminator, right?
Yes.
Well, it is trained using different objectives.
Which is not shown here.
Which is not shown here. It's just like it's just
Okay.
the generator now. Yeah.
Okay, so, sorry, I thought this was how you train it actually. Okay.
No, it's
That's
just
fair.
like working with Mikhail. Yeah. Question? No. Okay. So, like this is the final architecture, like the full architecture. You have 4 networks that you need to learn. 4 networks that you need to learn. So the generator and the decoder. The generator and the decoder. Yeah.
This loss does not have components for training the classifiers. Both C and
yeah,
D.
it's just for generator and decoder.
Should be
Well,
trained
the
separately.
discriminators, their loss is just to take both samples and try to discriminate.
Yeah, so basically what you use in for log density trick is kind of classifier.
Sorry, what?
The network that you use to do like the ratio of densities, the
Yeah.
trick with ratio of density is kind of classifier.
It's just a classifier between two
Not the kind
types
of
of
classifier, this is exactly classifier.
Like here you have latent data it classifies between them, and the same here. Well, just ignore for a little this part. Like there is some tricks, there are some additional tricks that they use, like adding the generated data to the full loss.
Wait, but
Yeah.
I'm still confused. So this is not an ALPA, right?
It's like an approximation. Well,
I'm not sure. Because if you consider, well, the last term, this is some kind of approximation for KL divergence in ALPA,
yes,
right?
Yes.
So the first term should be data term. But it,
First two.
First two is the data term.
yes, the first two, but I think that it is only the first term, which is data term, not the second one.
No, and the second one, the first term is the data term from Via,
Yeah.
Right.
and the second one is the data term from GANs. They have both.
Yeah, and they just
They
sum
just
them.
sum. They kind of
Approximation is the sum of the. Well, actually, when they train, I think, encoder, they ignore this part, just do these losses.
When they train encoder,
Well, while they train encoder, yeah. So this loss is for the generator. Because we cannot, well, when we used our trick, we said that this part doesn't depend on theta, but it
Right.
does depend on theta, and you cannot use it because of this.
What is Z and beautiful Z? Z with head and beautiful Z.
Beautiful, that is just perfect latent variable.
that's why it's beautiful.
Like, and this one you take data, yeah, you take real data, encode it in distribution over this.
So do you understand right that beautiful Z is Z from prime,
Yeah, just some Gaussian.
just some standard Gaussian distribution. So let us try to understand what group of parameters is trained during what step of the process.
Yeah, like they.
So we have 4 groups of parameters: theta, eta, phi, and W. Right?
Yeah.
Omega.
Omega.
It's not
Omega.
W.
Yes.
So they, when they optimize, they have 4 steps in each iteration. They have 4 steps. They train generator using this one.
All 3 terms?
All 3 terms, yeah.
The generator is what? This is G of Z, right? It takes Z and outputs
Output
X,
data.
synthetic X.
Yeah, but the last term doesn't depend on generator,
Yeah.
and where
So we shouldn't choose the last term.
Yeah, it's not used, right?
Oh, maybe we will just write down
Yes,
4
yes.
Yeah, yeah.
problems
I think we should.
in order to be clear.
And I also think we should say like which one is maximization and which one is minimization.
Exactly. Well, we'll do.
So I guess here the danger is that the objective might be separated into 2 pieces. This is Via and this is GAN, and there is no connection.
Let us see.
What is L1? It's like L1.
It's all one norm.
It's like
The
here,
first one. Yeah, okay.
like below are the losses.
Ah. квадратик, это 3 части.
I think it should be maximized.
Yeah.
Because you have minus error.
Yeah, this helps also.
Okay.
Both discriminators are trained using just one term. And what about encoder? It's trained using all 3 terms. Encoder?
No. No.
No?
I will write down. So it's max again.
I know. All 3 terms will depend on Peter.
Well, we cannot use this one. I will.
What's that? That's what?
Yes.
By using representation trick,
Yeah.
we'll get all 3 terms relevant. And this is probably the only group of parameters which depends on all terms. Okay.
Well, unfortunately, we cannot use the second term in the encoder.
Why not?
Is this cheating? Or is it like a clever
Well,
approximation?
I consider it as cheating, actually. That's why I wrote down like hacks and tricks.
Which is the second one?
Yes.
Which one?
Then, sorry.
Maybe we should just use some notation for the terms.
Well, I almost finished.
ABC.
C is already used.
ABD.
Yeah, D
First
as
and
well.
second term and third term. What's the problem?
Well, I'm not going to write down the discriminators because they just
Discriminators depend on single term, right?
Yeah.
But why don't we use here the second term?
Yeah, because here, when we replaced this term with this one, we discovered this part, which depends on theta, on eta. So we cannot do this if we
Wait, but
optimize.
it's constant with respect to z and does not depend on theta.
No, on eta.
It doesn't depend on eta, it's constant.
This
We
one?
may integrate
It's
z.
Yeah.
constant because x is fixed, right?
Z.
It's just log b star of x.
No, we have expectation over x variable here.
Yeah,
It
but,
doesn't
Yeah,
matter.
But
Because you have integration with respect to z of probability density, which is always 1. Because subintegral function doesn't depend on z.
Let me think. Well, they put this one in the paper.
This term.
Yeah.
This is what? This is integration with respect to z of subintegral function which doesn't depend on z. Right? So we simply move it out and get exactly log of p star of x.
Times 1.
it's outline.
Yeah,
So
the
this
whole-
means that this term doesn't depend on eta.
Okay, but
Yeah.
another one does.
This one?
This one does.
Yeah.
Yes, but this one we
Yeah, but
substitute.
then we throw away this dependence. So basically, this is the second term in
Earlier
the
you
equation,
switched.
and like this is like forgotten afterwards. This one,
Which one?
like the big one.
This one?
Yes,
And it still depends on eta.
yes,
And why can we ignore it?
because they're cheating.
But why should we cheat?
Yeah,
we can,
that's a good
we can
question.
compute it. What's the problem?
Two networks in there, it's kind of scary.
And so what we may still
We already have 4 networks.
we may still compute the gradients with respect to everything. So we may use representation trick here. We may substitute z as a function of eta, and we compute gradients with respect to eta.
Yeah, that's
So I don't
right.
understand.
Well, I kind of missed it, but well, I thought about this part. It was the explanation why it's not here. But well, in the paper, this is right. They optimized exactly this objective.
Maybe
So for some
we should
reason,
simply correct it.
yes, and
and
for some
get
reason
better
they
results.
just throw it away because it worked better.
I don't think that will be that simple.
Well, in the paper they said that not exactly this thing. We can now optimize theta because it's independent of it, and they said nothing about it.
Actually, it's independent of everything.
No, it depends on X.
No, I mean these four groups of parameters.
No, it's just for saying that you can replace the first term with the density ratio tree because okay, it's just explanation on why we can add and subtract this expectation.
Okay.
And then just discard the second term in the first term.
This is good remark. But still, this is only reason to ignore the last term, the log of p star. But not to ignore the second term in our criterion when we optimize with respect to eta.
So there might be some sort of optimization issue because, yeah, hard to say, but probably they just couldn't train it this way.
Something probably blows up.
Well, stabilized optimization here could be rather harmful because you have 4 criteria and you should optimize everything correspondingly.
That looks like nightmare actually, like 4 criterions and then moves in different directions. Maybe just for the stabilization. I don't know.
Do they have some regularizations like that the difference between parameters on sub-steps on one step should be close to the previous
They use
something?
Adam most likely.
Yeah.
So it's like it's kind of they use Adam most likely. So there is momentum inside. So it's kind of
No. Momentum is for the parameter for one network, and we need some correspondence between parameters of 2 networks on separate neighboring optimization steps.
Why do we need it?
Because otherwise, if we change at a big value one network and stay everything at the same value, we got the better results.
Yeah, but they do like stochastic optimization probably on one group of parameters, then another step on another, and like they iterate. So
It's not enough. It's not enough.
Well, I think they just fix it by very low learning rate.
And escaping from some terms in. Okay.
On the picture you have 3 arrows to discriminator.
Yeah,
and,
right.
Does it try to distinguish all the data, all the input data between x real and x reconstructed, x real, x generated, and so on?
So it's actually one of the tricks too. They put real data versus reconstructed and generated data. They mix these two, like in the data set. And
so we don't want to distinguish between reconstructed and generated.
yeah, they're considered the same.
Can you explain like what's the point of C? Because C kind of the C latent discriminator. What it discriminates what from what? Is it like
encoded data and encoded latent variables and prior?
It's like a regularizer.
Yeah, it estimates
Something
the kind of divergence.
It ensures that even more generalized with respect to inference network, we should get prior distribution.
Yeah. So like here.
Some analog of KL divergence.
Yeah. Something like regularization. We have something like regularization here, and it just approximates it.
And why not to put KL divergence as well?
Because we have
Because
implicit model.
we will need to make assumptions on this Q.
And now, as a Q network, as a inference network, we were using what?
Just network.
Well, which simply generates Z. So this is it some kind of implicit probabilistic model? So we have a neural network which generates Z, but we do not have access to to its density.
Yeah. We just know if we take data.
So this is some kind of sampler from Z. And in order to be able to compute this KL divergence or any kind of its approximations, we have to train a separate classifier which returns us this density ratio,
Yeah.
which is enough for estimating KL divergence.
Yeah.
Because to estimate KL divergence, we need to be able to do two things. First, to generate samples from the first argument of KL divergence, and second, to compute log density ratio. And to compute log density ratio, one way to do this is not to be able to compute both densities, but to compute only classifier which returns density ratio.
Yeah.
So this is the key idea of the paper.
Yeah, but for that
And
one,
if this method really worked, that would be a breakthrough in deep learning. Unfortunately, according to many indirect reports, it doesn't work so well as it seems to be.
Yeah, like
And also, like,
they used some hacks to
Another comment, it looks like in this model, it's not clear like how to generate new data, because there are like, what is P of Z? So they only have like conditional distribution, so they only have Q, eta, Z given X. But like if you don't have X, like how do we get Z? Like what is the right Z?
how to
Prior?
generate from this if we don't
No,
have
how,
X, right?
if you just want to generate a new sample. Like,
yeah, but this is the
prior.
same as in variational autoencoders. You just
No,
sample
yeah, sample
from
from-
prior.
From prior, but where is prior?
Prior is just some Gaussian distribution.
Ah, so there is prior.
Yeah, so
It
P,
is a Gaussian in the end.
like,
So the KL term
Like
comes
here.
from a discriminator, which like discriminates between samples from the prior and from the condition from the posterior.
Yeah, but then I don't understand. If you have a prior like, which is a Gaussian, why do you need to like to have another discriminator like to say if a sample is from a Gaussian? Why can't you just compute likelihood of that of a Gaussian?
Because the posterior essentially like it has the same structure as a generator of GAN. So it takes some noise, it takes X, and it produces a sample of Z. So you don't know the density of this particular sample.
Yeah, but
Yeah, but we know this
you're
too.
comparing this against the Gaussian. So if you compare it against the Gaussian, you can always do like just density.
Yeah, you can, but would that be principled? I mean, you want to start with elbow and replace the interactable parts with something tractable.
Yeah, but like if you want just like if this piece is a KL in the Z space and like one side inside KL one thing is a Gaussian, then like it's kind of it's weird to have a discriminator there. This disambiguate from a Gaussian.
well, you can calculate one likelihood, how
no.
you calculate KL divergence.
Unfortunately, this is a very good question, and we've met it already several times in different formulations. So the question is, can I suggest something better than training classifier in the case when we have two-class classification problem, and we have unlimited sampler from one class, and you have a closed form expression for density for another class, and you would like to build a classifier. So what is the best strategy? So as far as we know, probably the best strategy, although it still seems quite ugly, is to simply sample from the second class. Sample a set of objects and then train a usual classifier. If you can suggest something better, well, please do. And I will be happy to discuss it with you afterwards. Because this is an important problem.
So basically, like I'm confused somewhere. So why is it not just a likelihood, like of sample from Q with respect to like a Gaussian, like L2 distance to the center?
No, what you're saying is cross entropy, and KL divergence is like second term. Just take a look at it. It has the density of a Q, right?
Okay,
need to know
it's
the
because
object.
it's different direction.
Yeah, what you're proposing
that's
has a potential problem of being just a point at the maximum probability of the prior. It doesn't give you any error for shape of the approximation. It doesn't control entropy of the approximate posterior.
Okay, but I was just worried that like this thing is implicitly doing the same thing. Yeah, but then the KL is in different direction. Okay.
So if it's in the right direction, it's not elbow.
It's not double in both directions, right? How can you compute it if you don't know the density of one thing?
Well, you can sample from one thing. You have.
If we do not access to any of the two densities, we have no choice but to use density ratio tree. This is our only option.
Yeah, but like here, like we know P of Z. P of Z is a Gaussian.
But not the other one.
Yeah, not the other one. But like
Even if we reverse the arguments in KL divergence, we would still have no choice but to use density ratio.
No. Like then we would be able to just sample from P of Z, which we know, and then just it would be like likelihood of another one on on the sample points. And that's it.
Why?
No.
Yeah, still density Q. You will need to evaluate.
Yeah, but Q is parametric.
No. Q is only sampler.
Yeah,
You can only sample from it. So our neural network, inference network, produces sample Z, but we do not have access to its density. And that's important because this allows us to use much more elaborate Q distributions.
Okay.
So to do what to calculate this thing, we need to be able to actually invert the Q et of Z. Like we have a sample Z, and we need to know the density of Q for that sample. So this basically means that we need to invert the distribution.
No, it's the same as here. We don't have it. We can use it.
Same problem.
Okay, we have discussed density ratio tree.
Well,
Let's continue.
Very important part of this AlphaGAN architecture. So now, like I have some comparison between this architecture and the others. Well, they are not so impressive. They show just like comparable to other modern GANs. I suggest that we just look fast through them and discuss a Bayesian GAN very fast. So, like some metrics, compare with DC GAN, BayesianGAN and AlphaGAN. Well, they show that samples are comparable in terms of stability, in terms of mode collapse.
What is this metric? What's the Wasserstein distance between what?
Between the real distribution and the generated distribution.
What is H?
H is adversarial generative encoder. I think if we have one author here on this paper, like some modern GAN state-of-the-art architecture. And this box plot, they train different GANs with different hyperparameters. So this variation is due to hyperparameters.
But this is negative Wasserstein distance. So the larger the better.
The larger the better, yeah. It's the same on all the graphs. So, like, the good thing is low variance. It's not very sensitive to hyperparameters. Well, sometimes it's not very low.
Isn't it like kind of weird? Because it depends like what are the hyperparameters.
Yeah.
Because sometimes you can say, oh, this is one, and
yeah,
another method this could be a hyperparameter, and this could be sensitive.
Just plug some bad hyperparameters here and you have a large box plot. I don't know. They just said they variated hyperparameters.
And what is
the GAN GP?
It's the GAN that optimizes exactly these distances because it's the best.
And what is GP? What GP stands for?
Granular penalty. It's improved Wasserstein GAN. So, similar graphs for other metrics. First one is structure, similarity, diversity. They take different samples and calculate how far they are. The larger the distance, the better. And these two are the inception scores of the generated values. They take the inception network and look how good is the recognizability of the samples and how good is the diversity with respect to each class.
How did they specifically compare to different samples for diversity? Just L2 norm, L2 difference, or?
In the first graph?
Yeah.
It's like some distance. They take samples and calculate average distance between them.
Distance in pixels.
Using some different metrics, like structure. It's called structural similarity.
But it's a metric directly on pixels, and it doesn't have anything learned. Yes.
Yeah. Like it doesn't depend on anything. Just some metric that probably corresponds to
on pixels.
On pixels, yeah.
Well,
it's more complex than just L2. It calculates some variations of the pixels around points and so on.
Why age is worse on all the graphs?
I don't know.
Because it's my paper.
Well, maybe you can explain.
Yeah, the code I uploaded to GitHub doesn't work for some reason.
Well, for the code that does not work, it shows surprisingly good performance.
You mean like
not better than they, so it should be.
Well, their message is that their architecture is comparable to others, like not the superior. So now I show you the samples. They about those two, they say that AlphaGAN is definitely better, if you can see this. They take MNIST and color it in random colors. It's like more diverse MNIST. Harder for GAN.
That's a new word in this experiment.
Yeah.
I have seen, for example, like two digits means they have two digits and put it like one on top of another. That's like a two-digit list.
Yeah. Well, the next example for faces, this is one is easier. They say they're similar, well, comparable. Okay, so something like a bottom line for AlphaGAN. That's some good architecture that used interesting tricks that possibly can be applied to GANs and other areas. But the problem is still needs some tricks, so probably we need to do some further research in this way. So,
where are the advantages? Where are they better than others?
well, yeah, as I said, I'm not going to show you some impressive images. It just learn some GAN that is comparable to the other GANs. Well,
They're very good in columnist.
I think
Yeah.
the advantage should be that you actually have the encoder network, which you don't have in GANs.
Yeah, but there is adversarial learned inference.
There are very much lots of architectures that have this. Well,
Yeah, this
it's
is
hard to
Or
compare.
maybe-
They're worse. They lose image quality. I guess that's the problem. So it's like
Well, they don't have comparison.
Something goes away.
Well, that's
Something
interesting.
So that basically they compensate for multiple hours, but they lose something else. So I guess here the point is that they claim that they didn't lose as much.
Well, I don't remember the reconstructions in the paper. Maybe they decided not to show them. Or like how good the encoder-decoder works.
Yeah,
I'm not sure.
So each time you establish an encoder, you have to pay for that. And the price is the quality of generated images.
The quality of reconstructed images.
maybe that's generated as well. It goes like all together.
That's interesting. I wonder if there's some objective reason for that.
Maybe like this, like if you want to like cover all the modes, you don't have enough capacity, and then you start losing precision in some sense. Maybe, but like no.
Yeah, maybe.
I think they like have key images and they also have elbow, which you may use for like anomaly detection or something.
Oh, yeah, right.
But it's not true actually, because in practice you never have a lower bound. Because you cannot train this density ratio up to the end. Right?
Yes, so this is approximation, but this is not a lower bound more.
Yeah,
but I think it's
Yeah, but why can't you, like, all these density ratios, why can't you just, like, if you're not talking about training with it, but we are talking about estimating a quantity, why can't you just train it like 10 to convergence?
Well, because
you cannot prove that
numbers for like non-parametric discriminators, like the perfect discriminators.
Yeah, but like if your discriminator is big enough, isn't it perfect?
Well, you cannot be sure.
I think if it's big enough, then you will have like 1-0 predictions from your classifier all the time.
Also, in the formulation,
Okay.
in the formulation they presented, they have two terms for the reconstruction error, and they are not weighted appropriately.
Yeah, not the appropriate sum of these terms, right?
I have a question about training classifiers. So we have infinity samples from prior, but limited from real distribution. So what is the optimal strategy choosing the fraction we put? So we take 50% from real data and 50% from samples to train classifier.
Well, if you have a large data set, you can imagine that it's infinite, but you cycle through it, and the latent variables just random every time. So you take one current batch of real data, you take random batch of latent variables, and that's it.
Or I have a better idea. If we get back to the density ratio trick, we assume that the priors for both classes are equal. If you have class imbalance, you could adjust the prior probabilities for class accordingly. Here,
well, it's infinity versus bounded. How do you adjust? You can generate infinite samples from latent variable. So they decide just to generate equal amounts, and that's it.
And we use the classifier among legend in legend space to estimate P star of Z.
To estimate scale divergence in the latent space. This one.
Well, I have another question about log density tricks.
Yep.
This thing. So basically, like it uses classifier as it estimates probabilities, but are these probabilities calibrated in some way?
No.
No way. You just have anyone tried to make them calibrated, like to do something to make it calibrated?
Well, if you use cross entropy.
Yeah, but it's not calibrated.
Well, you can take any correction strategy for SVMs. And there you go. That's calibration for your probability, because I mean it's exactly the same problem as calibration for example, SVM. You have some kind of probabilities, but they're not actually probabilities.
Has anyone tried to put that into GAN training? Calibrate probabilities, like something?
They should have made some kind of calibration, otherwise the log can be a negative argument.
There is one more issue. Imagine that we have managed to
put sigmoid. It's 1 from 0 or 0 from 1 and 2.
Imagine that we have managed to build this density ratio estimator, right? And we have access to one of the two densities. Then it seems that it seems quite reasonable to take this density, to multiply it by density ratio estimation, and to then we should obtain something like the first intractable density.
Yep.
But the problem is that it is not normalized. I have no guarantees. So it can be 1,000 times larger or 100 times smaller than the true density.
But also because this is expectation of the density tree, of the log density, not pointwise thing. It's not an issue.
No, this is an issue. This is an issue that any kind of, when our density ratio estimation is not perfect, we can't guarantee that the first density will be normalized density, even if we have access to the second density. So the only case where we can guarantee is when our density ratio estimation is exact. But this is all possible only in theory. Okay, let us proceed to the second part.
So the second part is BayesianGAN. I will talk about just one part of it, like how to train the generator, not about... then you have another interesting part about semi-supervised learning. I will skip it, how it is. You can look at it, it's very interesting. So the BayesianGAN has very simple architecture. As I said, they want to learn some distributional parameters, and to do so, they introduce this generator and discriminator, some networks with fixed architecture, and they want to learn distributions over those parameters. And as I said, in order to generate a new sample, they generate a network, generate a latent variable, combine them both to create a sample. So, like, now we just define those posterior distribution. We want to learn one distribution over another. So, if we have a discriminator, we want to have distribution over generator parameters. We say that the best generator parameters are those that full discriminator. Like, we take those parameters of the generator and test your discriminator, test your generator samples using these parameters. And in reverse, if you have a generator and you want to train a discriminator, you want to distinguish between them. You have those probabilities of real data, probabilities of fake data. This one is very similar to like simple GAN objectives, but are in this likelihood form. Is there something clear on the slide? Okay. Like why do we do this?
So this
both
is
equations are not obvious.
It's strange to give a posterior distribution. We usually start from the joint distribution and get posterior.
Looks like more like a joint, right?
Yeah, that's interesting.
This is just the denominator of the Bayes theorem.
Should be. Well, so we have prior and we have something like likelihood, right? Why likelihood looks like that?
Well, if you try to write this posterior distribution using Bayesian formula, it doesn't look like this, and doesn't look like something you can use. So they just say the posterior will look like that, and from it we will infer those.
But is there any kind of motivation why posterior should look like that?
Well, the motivation is that, like those parts about intuition, we define posterior like that because we want generator to full discriminator. We define posterior for discriminator because we want to distinguish, and then we infer everything from it.
Isn't it just explanation of our loss?
Exactly.
Yeah, that's it. Well, but we want to look at it in terms of posterior probabilities.
Well, any kind we're dealing with the loss, we think of the loss as some kind of log likelihood, as a negative log likelihood. And then you would take minus loss and exponentiate it, then we get some analog of a likelihood function.
Yep.
So this is exactly what Kirill said. Yep.
Well, but they decided to use those posterior instead of joint.
Well, these sets are fake or like real?
Sorry, which one?
These latent codes, are they real or fake?
Like here we have very simple GAN architecture. You have just latent codes which are taken from prior, and you have data X, which is just real data.
Okay.
So here the prior generated from prior latent codes.
But why then do you say that, like, the first expression is larger than you full discriminator? Where does this?
You take latent data, pass it from generator, get samples, pass it to discriminator. It assigns high score to it. And
so discriminator thinks that these are real images.
Yeah. And this
is exactly what we would like to obtain for our generator.
Mm-hmm.
So then it looks like a reasonable likelihood function. And here we also have prior distribution, so we end up with a posterior optimization constant. So,
well, if you
yeah.
take a log of this, it won't be like exactly the regular GAN loss?
Yeah, it will.
Well, you ignore the
very
prior. Yep.
Yeah, that's very close. I think they motivated this by just regular.
How do we take the prior?
Well, prior, I think, again, some Gaussian prior.
Weight decay.
With just some hyperparameter, we can change. Yeah.
But we need to specify sigma for the weight decay.
That is not the
like
the big problem.
Just another hyperparameter, right? Yeah. Well, actually, this is the most important slide in this BayesianGAN architecture because that's it. That's the full architecture.
And what's the method?
Yeah. So the method is just we sample repeatedly from these distributions, and we output some samples as a distribution.
Is it easy to sample from those
No,
distributions?
it's very slow. It learns like 10 times the DC GAN. Well,
so we have to use scalable MCMC methods.
And why do you use a hybrid Monte Carlo here?
Because we only have two scalable MCMC methods: hybrid Monte Carlo and one-given dynamics.
And one another.
Hamiltonian Monte Carlo.
Hamiltonian. This is hybrid Monte Carlo.
Oh well, they use this method.
So okay, we sample from both distributions, and so what?
So you take some random discriminator distribution and sample iteratively, and you output you have some sequences of samples, and that's it. That's the distribution. Like final parts of these samples.
But what's the objective? Like log likelihood? What do they optimize?
They do not optimize anything.
Yeah.
They perform some kind of Bayesian inference.
Yeah.
So they run some kind of sampler, dynamic scheme, which ends up with the samples when it's warmed up from posterior distribution. And those samples are the answers.
And how they generate new samples?
New samples to like
new
drop.
axis.
New axis. They take random generator from this sequence, plug it into network, plug random latent code into network, and generate and pass it through network.
Random, only one. We do not integrate all of them.
If we want one sample, we take one network, one latent code, and it's one sample.
One network, one code.
Well, it's really weird, this procedure, because essentially if you think about SGD as performing some sort of Langevin dynamics, like some sort of sampling, then essentially you can just perform normal SGD training for GAN and then just save the intermediate parameters for your generator and discriminator. Then you just say, okay, those are samples from my posteriors, and then I just take the random one and
well,
do this.
but this is not true, because if you come to some mode, probably you want to stop training, you can go to another mode, already having good mode there before. Well, you mean like the same, but
yeah, but also you need special thing parameters with SGD. For example, if your linear rate shouldn't go to 0, you should like to be able to basically to look at SGD as a sampler, or something has to happen with SGD. It shouldn't be like regular
SGD itself is not a sample. We were discussing that today. This is a sample from very specific distribution, which is not the posterior distribution here. So to get sample using using SGD, you have to use stochastic Langevin dynamics. This is a bit different from standard SGD. Here, instead of stochastic Langevin, they're using stochastic Hamiltonian.
Well, people also use circular learning rates when the schedule looks circular, so that the learning rates get high every several number of epochs. And they use that to ensemble deep neural networks to do snapshot ensembling.
Well, that's essentially the same, I think, yeah.
It's kind of
like it's
there is the direct connection. It's kind of a bit long analogy.
Can you start not from random feed, but from like a trained GAN, like from a mode?
Well, I think that's a good idea, but they didn't do it. Maybe they were afraid that it will already be stuck in some mode collapsed minimum.
And why we use just one network and do not integrate over the parameters?
Probably because we do not have memory to keep all these thetas.
No, they do actually keep them.
Thetas.
How many? 10? 100?
Well, as many as they need to generate diverse samples. So they say that the result of the algorithm is just this way, just
Yes,
this sequence of thetas.
But it is somehow like connected to like AutoGAN of Ilya, in the sense that the output is like a collection of networks.
Yeah,
and then like they don't have like manifold structure, so they cannot really interpolate between GAN samples.
Yeah, yeah. Well,
like,
they can try to integrate, I think, over this one. This.
Yeah, but they have to like integrate. No, I mean not integrate, but interpolate. So that's because like usually like what often people do with GAN, you start with one correlated code, you go to another code, and then you see some reasonable features in the middle.
Not always, but here I think you mean interpolation in the space of weights, not in the space of code.
No, but like to be able to interpolate in the space of code, you have to have like one network, like one generator. And you have a collection of networks. Then like how do you like interpolate? How do you jump between them in the middle?
That depends on how you're using the ensemble of generators, and that's a good question. I know how to generate image from one generator. Now I have say 20 generators. So what should I do? Should I take one by random, or should I use all 20 generators, and then what should I do with the resulting images?
That's a good question.
It's just about generating that way. We don't need to integrate over all the samples. Well, if we want to generate one fake sample, we have tools to distribution. We take 1 point from each, and that's the result.
But this is not the result of ensembling of generators. This is just one randomly picked generator.
I will write down like.
So this is no, there's like no ensembling effect, except for the effect that we do not, or we presumably should not have mod collapse here.
Well, why? I don't understand why do we need to integrate over all this one and don't need to integrate all those one?
Because each Z is responsible for a single object. We do not have, and we should not integrate with respect to Z. But generator, now we have continuum of generators.
Yes.
So according from Bayesian point of view, I guess we should somehow ensemble them. So we should take an expectation with respect to this probability over the weights of generator.
Will this be will be average sample over all the generators?
Yeah, but okay.
I would say so.
That seems correct, but it will probably be like
Yeah,
very
but,
blurry.
like when you do, say that you have like a mixture of Gaussians. When you sample from it, you pick like one component and then you sample from that component.
Yeah, exactly.
You don't sample from all the components and average. You don't do that.
I do not do that.
You just need to think of this thickness as a fixed ensemble. Suppose you do have this posterior or something, that Bayesian distribution over thetas. We just sampled some thetas from it using the HMC and keep them fixed. Yeah, that would be less flexible. Well, it's not clear whether it would be less flexible, because from one side you have kn times size of theta parameters. That's a lot. But you have fixed number of models. So at the test time, you only generate samples using those n different generators. Whereas in like fully Bayesian approach, you would be generating a different network each time you sample.
Right.
But that would be coming from some other network having finite capacity. So in the end, it's not clear which one is better. The full Bayesian approach might be better, but unless it's conditioned on something, I'm not sure it would give you a lot of benefit.
Well, me either. The question is, well, I have some kind of theoretical interest. Whether it's potentially possible to get on something or not. Because I don't see how. We have a posterior distribution over in the space of generators. But I do not see how we can ensemble these generators altogether. I know how to perform assembling of classifiers, of discriminators. But I can't understand how we can perform assembling of generators.
Yeah, but like, say we are talking about Gaussian mixture model. So like you have a posterior distribution on your weights, on your parameters. Like, but when you are sampling, you're not unsampling. You're picking like one component at random and then sample from it.
Yes, but I'm not sure that this analogy is fair here.
As far as
something different.
As far as I understand, we don't want to make too much averaging, because what we want is we want to get localized output of diverse models. If we average an ensemble, it's good for ensemble learning because we average out the mistakes. But here we want more diverse output. So if we average among many models, we get one and the same grayscale image in the middle.
Yeah, that's true. But we're trying to understand why we do this. This one seems incorrect. Like what you're saying is correct, but when to ground it theoretically, why do we do so? Well, I have a suggestion. Maybe there are two ways to look on this distribution. First way, if you look at it like we have data and we condition, we find those weights depending conditions on the data that you used to learn. Like you cannot learn, you have only one generator and you learn distribution given the data. And they doesn't look like this, they look like there is some unknown prior distribution that, and they want to approximate it, not given the data, but just another latent distribution, but over networks. So like real data is, they say that real data is generated in the same way, and they want to find those latent variables.
I think sampling corresponds to like approximating the expected value of x.
Yes.
Given the distribution over like posterior distribution over networks, right?
Right.
But why do you want to compute the expected value of x? Why do you think it's a good idea? I mean, you can sample from this distribution, like you can sample from the distribution on x, which is like g of x, g of z is a distribution because you have a distribution over g, right? So you may sample from this distribution, or you may compute the expected value, but it's completely non-obvious why expected value is a good idea.
Okay, what you have on the next 7 slides?
Like I have
examples. And before we passed on, I have a small question. How you would compare this approach and the approach when we just train multiple generator discriminator pairs from different initial conditions?
Yeah, that's a good question. I think this must be more like proper way to train an ensemble, because there are dependencies between the generators and discriminators that you learn. You just sample from those distributions, you have this distribution, and if you learn the ensemble, you just pick random points and learn independently from those random points. But that's not clear if this architecture achieves this proper way to.
Well, another
Yeah.
important point was already mentioned. If you just train GAN using SGD, it does not necessarily mean sampling from the posterior. Whereas here we sample from some posterior. It's not clear what probabilistic model it corresponds to.
Yeah.
But
well, you can train random GANs and say that it's the same
you can,
approximation.
but
like take the data, put some random conditions in different ways, sample from data, get the ensemble of GANs.
So
Well, it's not clear which is better.
Can we say that this approach is equivalent to having multiple generators and discriminators, plus some sort of penalty for them being too close or something like that?
Well, I'm not sure about the penalty of being close. It's just, like we rely on this one to generate.
Yeah, I'm just saying that there are like this diverse inference where you try to have like several points from your from a probabilistic model which have high probability but which are far from each other. And essentially, this paper tries to do specifically that, as far as I understand. And
yeah.
Doing sampling to get these high probability distant points is not very efficient. You might want to do something different.
But are you sure about like different points, maybe simply points from the distribution network? From the distribution.
No, like if you want to have diverse samples,
but
you have to add something.
I'm sure that they won't do.
Well,
yeah, but
the question
one step is just remove correlation between neighboring samples, and second step is add more diversity on top. Because I think what this method does, they kind of remove correlations. So and like if you sample like from big distribution, but you get uncorrelated samples, maybe that's already diverse enough.
I see.
Yeah. Okay. So examples. The first row is BayesianGAN samples. Each plate corresponds to different network, like single value of this one, and the bottom one is 3 different DC GANs trained independently.
What are these
white
lines?
Like there are plates, 3 parts.
No,
not
this.
Well, I don't know. There's some artifacts in the paper.
why are they
have
blurry?
some issues in plotting it. I don't know.
But why are they blurry? Why are Bayesian GANs blurry?
They're not only blurry, they're gray. They're kind of grayish. We saw that effect on MNIST, where like if like networks are too small, then it kind of gets gray. It doesn't turn like white images.
Well, maybe because if they were big, they cannot learn it at all, like 10 times the DC GAN. Very hard.
10
or
times
they
the
could
DC
not
GAN is
keep
not
it.
that slow. That's
Could not keep it in memory, yeah. Right.
Yeah, by the way, how many parameters do they have in Bayesian GAN versus DC GAN?
0. Like, it's based in inference, right?
You mean the network? They said the same.
I mean, they kept n samples of theta. So, does that mean that the Bayesian GAN has n times fewer number of parameters than DC GAN?
No. Each vector is the same.
Okay. So they use n times more parameters and get worse samples.
Well,
they should have
they're more diverse.
Yes, thing.
Yeah, they're sure more blurry if that counts as diverse.
Well, no,
they have these vertical lines that are definitely absent.
I think the main point here is that they are more diverse in the thickness and like rotations or something.
This figure says exactly what Alexey tried to tell us. Like, look, different generators learn different parts of the data manifold. Like, one generator corresponds to thick images, another to thin images.
Yeah, but it's not very diverse for DC GAN. It's less diverse for DC GAN.
kind of
So the suggestion is that if you learn different GANs, it's worse than if you learn this one.
Yes.
Worse in terms of diversity, but better in terms of quality.
And how they became sure that the Hamiltonian MC is burned in?
I don't know, I think they just looked at the samples and stopped when necessary. Like, other image samples? Yeah, unfortunately they're quite low quality. But again, each plate corresponds to different weights.
Like kind of via type quality?
Which one?
Like variational autoencoder? Is it what they do? Is it
well,
similar?
I think variational autoencoders are much better.
Well, the main point of this picture is that just like diversity between different networks is big. You take one network, generate different latent codes, and they vary.
All of them are Bayesians? Bayesian GANs?
Yeah, it's BayesianGAN and AlphaGAN, different datasets.
How can we be sure that they're diverse then?
See, they're diverse.
I'm not convinced.
Well, it's the same as always in the GANs, like, look at it, it's diverse.
This is the price we're paying for the absence of objective metrics.
But
Yeah, well, actually, those are like objectively bad. So can you argue that? Those are just bad.
When we talked about AlphaGANs, we did have some objective metric of diversity, so it should be possible to calculate at least something to say like, hey, this generator outputs something different from this one.
Okay, I think if you compute any reasonable metric on this, it will say that this is bad. So like,
but maybe it will be quite diverse.
Yeah, okay, but like, you have to really marginalize out quality. It is like,
that's true, that's true.
Diversity only.
That's true. Well, the other slides are about semi-supervised learning. I think I would want to talk about it. It's just another application of this BayesianGAN, which actually gives good state-of-the-art quality compared to this, no, but it's not about generating samples.
What if you train a normal GAN poorly? It would probably also be diverse and will also have bad results.
You mean poorly, like not converging? Or
yeah, not converging, bad architecture, anything.
No, bad architecture is not diverse and have bad quality.
So just take a bunch of undergrads, give them a homework to write a GAN. There you go.
Have your own cursor.
Well, this approach definitely needs some research. I don't know. They need to improve their methods, definitely. But the idea that you can just sample from distribution set using one network is already interesting.
Okay,
so
as far as I understood, the more Bayesian you are, the more blurry you generate.
The more uncertain you are.
Exactly. But this is the key issue, Bayesian.
You wanted some uncertainty? Here it is.
I haven't seen where
I'm not sure.
I think not.
This is just prepared. But well, the paper is a bit raw.
Yeah, they just.
I mean both
softly
of them.
speaking.
And AlphaGAN.
No, AlphaGAN is just very new. I think they haven't submitted anywhere yet.
Is it accepted to NIPS?
Yeah,
I don't remember.
They were online like June, July. It's kind of not that new.
And it was in NIPS format. Then also quite suspicious. But they have at least submitted to NIPS.
Yeah, but BayesianGAN is something around February, I think, and they just said we wanted to show you
the paper is not ready.
The idea. Paper is not final.
Maybe it doesn't work. We also have discovered a couple of mistakes actually in BayesianGANs.
Oh.
Yeah.
Okay.
I don't remember now what were those mistakes, but I remember that if I'm not mistaken, we did it with Musketeer. Professor Molchanov.
Yes.
Did we discuss BayesianGANs in spring?
We tried to.
Didn't we find some mistakes there in mathematics?
Well, one disadvantage was that the posterior distribution that they define depends on the size of the batch. and it is quite strange. So you change the Bayes size and you obtain completely another posterior distribution, for example.
Wait, but doesn't...
I think there was something, some more issues. Oh, anyway, let us simply state that this paper is not ready yet.
Yeah.
Although it contains, well, some